And we're back. This is the last podcast for Unit 4. We're going to deal with enthalpy of formation, which we symbolize with delta H sub F. So this is the heat that's involved in the formation of any product, a compound, right? So it's based on the standard state of the substance, and we don't want to be confused. The standard state for gas is not the same as the standard state in thermochem. So this is 25 degrees Celsius or 298 kelvins. 298 kelvins, and pressure is the same, 1 atmosphere. And of course, molarity would be 1 molar concentration. So that's what we mean by standard state. 1 atmosphere, hey, look, I already wrote it down, 1.0 molar. All right, standard conditions are represented by a little circle. So you're going to see this over and over. If you see this little circle-y thing, like for energy change, or heat change, or even Gibbs free energy change and entropy change, then that little circle just means, hey, we're under these conditions. So enthalpy change then would be our delta H, and we would call it delta H with a little circle thingy, right? And that means all the reactants and products are in their standard state. And the heat of formation is delta H sub F. Heat of formation. So we're going to form that compound from its elements with all substances in standard states. That's just what that means. All right, you'll have to use Appendix C in the back of your textbooks to get the values for heats of formation. They're published in lots of places, so if you want to Google it or whatever, that's okay. I just happen to know it's in your textbook on page 1123 to 1125. And the values are all reported for standard states. 1 mole of a substance at 298 Kelvin. And they're only reported for compounds. You won't find the heat of formation for any element because elements just are. We don't form them from anything else. They exist. So like copper, oxygen, hydrogen, even sulfur in its standard form means S8. So we're not forming S8 from S sulfur. S8 is the element sulfur. All right, hope that's clear. And then for any element, we always assign it a value of 0, right? Because we don't form them. And then the values for the elements and compounds get to be used along with Hess's law to determine things that we don't know yet. And here's how that looks. We take the sum of the products times the moles from your balanced equation minus the sum of the heat of the reactants. And of course that is also adjusted for moles in your balanced equation. So you've used this law before. Let's make sure you still know how. So here we go. Example 1, what is the standard heat of reaction for the combustion of hydrogen sulfide? All right, so heat of reaction means we're going to use heats of formation to come up with the heat of the reaction using Hess's law. Here's the data from Appendix C, and let's write that down. Heat of reaction is equal to the sum of the heat of the products. All right, so heats of formation of products. Hydrogen sulfide is being combusted. So let's have a balanced equation for that. We're going to make SO2 and H2O. Right, like burning a hydrocarbon makes carbon dioxide. Burning a sulfur hydrogen substance makes sulfur dioxide in water. And are we balanced? Sure enough. Already balanced. Well, that was easy. All right, so we'll take the heat of formation for the sulfur dioxide and the water, and there's just one of each, so we don't have to do anything fancy there, minus the heat of formation for our reactants. So that would be hydrogen sulfide and oxygen. All right, so let's do the math. The heat of our reaction is going to be, let's take sulfur dioxide, 296.8 kilojoules per mole, and we're going to combine that with water. negative 241.8 kilojoules per mole. And it doesn't give us the state, so what did I pick here, liquid or gas? I'm not sure, quite frankly. I don't remember. Look in your Appendix C and you'll find out. All right, and then we're going to subtract that from the hydrogen sulfide, negative 20.1 kilojoules per mole, combined with oxygen, which is 0 kilojoules per mole because it's an element. All right, time for a calculator. Here's my calculator. So let's see, negative 296.8, and I did it again, negative 296.8 plus a negative 241.8. So my products have a sum of negative 538.6 kilojoules per mole. And then the sum of my reactants is pretty simple, right? Negative 20.1 kilojoules per mole. So be careful with your signs here. We're subtracting a negative. And again, subtracting a negative means we're adding. Just had to think that one through. 518.5 kilojoules per mole, and that is negative, and that's the heat of our reaction. It makes sense that it should be exothermic, right? Because it's a combustion reaction. We should be releasing heat and light energy. All right, great. Let's do another one. In this example, calcium carbide reacts with water to form acetylene and calcium hydroxide. All right, that's the stuff that we use in a welding torch, right? Calcium carbide goes in and we get acetylene come out through our torch so we can burn stuff with a really hot fire. So we're going to use the thermochemical equation and the data in Appendix C to calculate the heat of formation for calcium carbide. How much energy does it take to form calcium carbide? So what do we know? We know the heat of the reaction to form acetylene is negative 127.2 kilojoules. All right, so I'm aiming to find this. Let's call this X. But I know that the heat of this reaction is going to be equal to the sum of the products. So here's my products, right? So I need to find out the heat of formation of calcium hydroxide and what's my other product? Acetylene. And so we'll find the heat of formation for acetylene, and we take away from that the heat of our reactants. So calcium carbide, I don't know, and then water, we have 2 of those. Any other stoichiometry to worry about? I think that was it, just the water. Yep, has a 2 here, and everything else is 1, 1, and 1. So the heat of my reaction is negative 127.2 kilojoules. All right, and I got my Appendix C right here handy. If I look in the calcium section, I'll be able to find calcium hydroxide, and I have it in solid form. Good. So delta H there is negative 986.2 kilojoules for every mole. And then we're going to find acetylene. So look under carbon, C2H2. Where are you? There it is, acetylene gas. Yep, acetylene gas it is. And that's a positive 226.77 kilojoules for every mole. Okay, minus X plus 2 times the heat of formation for water, and in this case I want liquid water. So you'll have to look under the oxygen section to find water. And liquid water is negative 285.83 kilojoules. Had to squish that one in. So now we're solving for X. Be careful with your signs, as always, right? So I'm going to go ahead and combine my products first. Negative 986.2 and a positive 226.77. So here I get negative 759.43 kilojoules. All right, from that we're going to subtract x and 2 times the water. 285.83, and that was negative. So subtracting the negative 571.66. All right, so let's make that addition, and we will combine that with the products. So pushing the wrong buttons on my calculator. So negative 759.43 plus 571.66. So that gives us minus 127.2 kilojoules equals negative 187.77 minus x. So now take this across and change its sign. And we get a positive 60.57 is equal to a negative x. So how do I solve for x? Multiply both sides by negative 1, and that just changes the sign of everything else. So that means that the heat of formation for calcium carbide is equal to negative 60.57 kilojoules. So you take what you know and what you can look up in Appendix C and work your way to the parts that you don't know. Yeah, that's it. I think that's it for the entire podcast. Let's see. Yep, that's all, folks. So study for your Unit 4 test, because it looks like you've got a test coming up. See you soon.